Okay, so we've graphed these several times. Exponential base e, it's going to go through, remember, it's going to go, they're all going to go through 0, 1, unless we've transformed them somehow. And then this would go through 1 comma the base, so that's going to be 1 comma e here, 0, 1 there. If we were to label this point right here, it's negative 1 comma 1 over e, because remember, when you put a negative in the exponent, it means reciprocal. So that graph's going to look something like this. It's got that horizontal asymptote out here of y equals 0. And then what does the negative do in front of the x? What type of flip? Horizontal flip. Flips x's, positive x's for negatives and so forth. So it's going to look something like this. I'm not going to take the time to label the points on this one, but we are going to say, because this one's growing and increasing from left to right, this is what we call exponential growth. And because this is decreasing exponentially from right to left, we call this exponential decay. All right? Now, today's topic on exponential growth, decay, we've got some Newton's law of cooling in here, which is kind of interesting. You do need a calculator in order to do these problems. You don't have to have a graphing calculator. But we're basically going to talk about things that behave like this, things that grow exponentially and things that decay exponentially. And we're going to show how we can use a nifty little formula that looks kind of familiar in order to solve these. Some of these problems are fairly complicated, some not so much. So this right here is what we call the law of uninhibited exponential change, okay, or the law of exponential change. So what we have here is we have A naught. That's how we say this quantity right here, A naught. This is the natural number E, 2.71, blah, 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 that big, long, irrational number. This is K, and this is T. So the things that I need to figure out is, what are A naught? I need to figure out what K is, and I need to figure out what T is. Now, what is T normally? Time. T is normally time, okay? A naught. Now, whenever I put a little subscript on something, it tells me I'm measuring that particular quantity, in this case A, at a particular time. So the time would be 0. So the way we say this is we say A naught, okay? Literally A, K, N, O, T, okay? So A naught, that's the initial time, or sorry, initial amount. So that right there is initial amount. Now, we did some problems the last couple days where we were talking about the amount that we put in an account to begin with. You could kind of think of this like the principal, okay? And then that K is normally an interest rate. In this case, it's going to be a growth or decay constant. A growth or decay constant. That's what the K stands for. It might be kind of nice if they used C for constant, but we use K here. C is usually used for some other things occasionally. So this is going to be exponential growth if K is positive, and it's going to be exponential decay if K is negative. Just like up here, if I had to draw something and I had to say, you know, there's a number in front of that, I could put a 1 there, and I could put a negative 1 in front of that. So that number that's in front of the variable in the exponent, if it's negative, that's going to make sure we've got exponential decay. If it's positive, that's going to make sure we've got exponential growth. Okay? So this is what we're going to use for the most part today, although we are going to alter that just slightly in some cases. So on example 1, there are some quantities that just grow and they never stop growing. Now, in reality, that tends to be difficult to find, but we can at least find it where it models that type of behavior, at least on the short term. So on example number 1, we've got a culture of cells, let's call them bacteria cells or something like that, that obey the law of uninhibited growth. They can just continue to grow and grow and grow and grow. And when things grow based on the amount that's present at any given time, like the more bacteria, the faster it grows and stuff like that, that's called exponential growth. So the formula for this particular cell is right here. Now, the nice thing about this is they gave us the formula. The bad thing about this is kind of a story problem. So sorry about that. Okay? But it does give us a description. It says, here's the formula that describes the amount of bacteria. It says A is the number of cells and T is the time in hours. And then we run through a couple of quick questions. It says, what is the initial number of cells? Well, we could find this two ways. We could look at this and say, hey, just a second ago we were saying that A naught, the number in front of the exponential, that's the initial amount. So if we said, hey, what's the initial amount of cells? It would be the number in front here, which is 75. So the answer here is 75, but let's think about it from another perspective and think about why they'd call this A naught, A sub 0, if you wanted to call it that. How many cells are there at t equals 0? We're starting a stopwatch and we're saying, hey, there are this many present to begin with. Let's just track how many there are. So when I start the stopwatch, if I plug in a 0, this would be e to the 0.25 times 0. That would be e to the 0. What is e to the 0? 1. So 75 times 1. There were 75 right when we started our stopwatch when it was t equals 0. Everybody got that? Okay. Next one. What is the growth rate? It is 0.25. Now you'll notice that kind of inherent in the question it says it's growth. How can you look at it and tell that it's growth? It's positive. Okay, if we were to be more specific so that we can understand how all these problems are going to work together, okay, this right here is A naught. That's the initial amount. We'd say K is 0.25. That's the growth constant. We know it's growth because it's positive. Okay. How many cells are present after 10 hours? How many cells are present after 10 hours? Is that a difficult question? No, because it gave us the formula. It says there are 75 to begin with, e to the 0.25 times the number of hours. If I put 10 hours in here and I throw that in the calculator, so I've got 75, exponential base e, and then we're going to do 0.25 times 10, close the parentheses. Really important to use parentheses appropriately. If you wanted to do 2.5 there, that would be okay. What do we end up with? Okay. Okay, approximately, and we'd probably round up, approximately 914. Or let's see, if they're saying the number of bacteria, let's think about this just a second. Should we round up? Can we have, what was the fraction? Can we have 0.687 of a bacteria? No. So we probably ought to round down. Now McKay's going to say, look, I've seen 0.68 of a bacteria. It's ugly. Okay. We're going to round down because we're talking whole bacteria here. Now, could we put a decimal here and could we make an argument that it's 14? Sure. Okay. But we'll go with this for right now. Any questions? Last question here. Now think about this. Here's our equation. We've got all the stuff we need right here. Now it says this. There are 5,956 cells present. How many hours have passed? Started out with 75. We let a bunch of hours go by, and now there are nearly 6,000. Can you figure out how many hours went by? Tylen's gonna guess. Tylen's gonna guess and check. We will see her next week after she fails the test. Okay, we're gonna solve this algebraically, and we're gonna say, look, they're telling me how many that we want. We know there were 75 to begin with. The only thing that's missing here is t. Does this look familiar? Yes. It does. This is like the problems we did yesterday when we were talking about money. It's like putting $75 in the bank at 25% interest, and we want $5,956. So, first step, divide by 75. Get that exponential by itself. Now, please don't change this to a decimal. Please don't change that. You're just going to have to keep track of a bunch of ugly stuff. Let's leave it like this. So I get 5956 over 75 equals e to the 0.25t. How am I going to get that variable, which is up in the exponent, down where I can work with it? We're going to take the ln of both sides. So if I take the ln of both sides, I get this. The ln of 5956 divided by 75 equals 0.25t. And what's the last thing I do to get t all by itself? So we're going to take this, divide by 0.25. Okay, that right there, I'm going to make it easy on myself. I'm going to circle that. That's the answer. Now, in order to answer the question, because nobody wants to be told the answer in terms of ln. Hey, buddy, how long is it going to take me to get this many bacteria? Well, it's going to take you ln 5956 over 75 divided by 0.25. Thank you very much. Okay? Type that into the calculator. Make sure you're using parentheses on this, and what do you get? 17.5. Is that pretty good? What are the units? Okay, they are hours. Now, I want you to stop and think about this for just a second. Okay? This just says it's cells. Let's hope that these are healthy cells. They're growing a new ear for somebody on some extracellular matrix. By the way, they actually do that. Or they're implanting a body part inside of a pig so the pig can grow it and then they can transplant it. Actually happens. Okay? We want it to grow really fast. Okay? Let's take a look at the next problem. What's the problem with example number 2 in comparison with example number 1? It doesn't give us the formula. But it does say this. It says it obeys the law of uninhibited growth. So it obeys this law, A equals A naught e to the kt. It says if there are 5 bacteria present initially. Well, that's good news because it tells us what A naught is. Okay? So that right there is A naught. Then it tells us some valuable information, and I want you to think about this because this is why we spent so much time on this yesterday. It says it will double in size after 4 hours. It's going to double in size. So if we start off with 5 and we let 4 hours go by, how many would there be? Good? 10. Now, we always came up with a 2 when things were doubling, right? Watch what happens when we do this. We're going to solve by dividing by 5. We get 2 equals e to the 4k. I'm going to write it as 4k. And then all I need to do is finish this up by taking the ln. So I get ln 2 equals 4k. So can you tell me what k is? Ln of 2 divided by 4 as a decimal. Let's get a decimal approximation for that. Okay. 0.17. Let's go a couple more places. Give me 2 more. 3.2? 3.3. Okay? Okay, now, this is really important. That's the first question. In order to come up with all of the answers here, we need to know what the actual formula is. We need to find this equivalent. So here's what we know. The growth constant is 0.01733. Or is it just 0.17? 0.17?
Yeah,
okay.
It's 0.1.
Okay. So here it is. There's the growth constant. And what that allows us to do is that allows us to complete the formula. So the formula we're working with is 5 present initially, e to the 0.1733 times t. Now, is this going to give us exact answers?
Yeah.
It's not. Somebody tell us why not. Okay, we rounded. If you wanted to, you could write this problem like this. You could say A equals 5 e to the ln 2 over 4 times t. Now, if you look how many decimals... What, dear? No, not because there's a 1/4 in front of it. Or it's been divided by 4. Careful with that. Okay? This, you have to write a decimal and 4 little numbers here. You have to write a line and an ln and a 2 and a 4. It's about the same amount to write. What would be nice about this in comparison with this? Okay, this would be exact. What if I said, hey, what's the growth rate? What's the percentage growth rate? About 17%. You can answer a question like that by looking at it in this kind of approximate form, as opposed to doing this right here. There are some advantages to having this be exact. This is pretty cool that you can look at it and say, hey, this is going to be at about 17% growth per, what's the time unit here? Just per hour. Okay. All right. Any questions? Sure?
Yeah.
Next one. How many cells are present after 17 hours? Put in a 17. So If I put in a 17, I've got 5e to the 0.1733 times 17. What does the calculator say? What is it? 95. Okay. 95 cells. What's the difference between that problem and the next one where it says present after 1 day?
Now you have to do 24 hours.
Now you just have to do 24 hours. So you can recall that command on your calculator. You're probably going to put push the up arrow.
How do you do that?
What?
3 seconds?
On yours, you hit, second enter.
Second?
320? So 320 cells. And how long does it take the population to triple in size?
Wouldn't you just put a 3 there?
There are a couple things we could do. We could say 3 equals e to the 0.1733 times t.
Or we could do 15.
We could do 15 equals 5 e to the 0.1733 times t. Or better yet, you could do 3 equals e to the ln 4 over, ln 2 over 4 times t. Ln 3 equals what? Ln 2 over 4 times t. And then to get t by itself, you just divide. So that means t equals the ln of 3 over the ln of 2 over 4. Is that all right? If you want to do it with decimals, that's fine. Throw that in your calculator. Or even better, 4 ln 3 over ln 2. That's a nice exact way to write it. What is it as a decimal? What noise was that? What's the problem?
How'd you get the 4 on the top?
That 4 right there? I used the exact one rather than the decimal.
Well, I know, I would go over.
Oh, this one right here. Complex fraction, I flip the bottom over and multiply.
Oh, smart, okay.
I've been working out. Okay, what is it? How long does it take? What is it? 6.34 hours. Now, stop and think about this for just a second. How long did it take to double?
3 hours.
It says in the problem. 4 hours. What if you let another 4 hours go by? It would double again. So the population would be 4 times. It would have quadrupled. So the tripling time's got to be somewhere in between 4 hours and 8 hours. Would it be smack dab in the middle? No. And that's because, everybody watch please, that's because exponential curves grow at increasing rates. So it grows kind of fast here, faster, faster, faster. Okay? All right, any questions? Okay, so let's look at the next problem. It says a population of rabbits at any time in t in days obeys the function 500 e to the 0.02 t. Anybody raised rabbits? Very good. What kind of rabbits? Holland Lop. Rabbits?
My neighbors raised one. I saw one new one.
There you go. Okay, enough rabbit stories. Okay, after how many days will the population reach 1,000? And after how many days will it reach 2,000? So let's take a look here. It started off at 500. So basically, what are we asking here? When does it double? So if I do 1,000, whoops, let me change colors here for this problem. If I do 1,000 equals 500 e to the 0.02 t, and I divide by 500, just like every other doubling problem, I end up with a 2 and then e to the 0.02 t. So I'll take the ln. I get the ln of 2 equals 0.02 t. So I get t equals the ln of 2 divided by 0.02. And roughly what is that?
34.66 days.
Is that wrong? That's right? Okay.
Not logically.
So
Well, how would it not?
it's gonna take a little less than 35 days, about 34 days and what is that, 16 hours or so for it to double. Now, that's how long it takes it to go from 500 to 1,000. Think about that for just a second. And then I want you to take a look here. Notice that when it doubles, didn't this always turn into an ln? And look what we're dividing by. What part of the original problem was that? The K, the growth rate, right? So whenever it doubled, okay, that doubling time was the ln of 2 divided by, make some room here. That doubling time was the ln of 2 divided by k. That's how long it would take. You may want to go back up above when I asked how long it would take to double on some of these and see if that works. Maybe it would work with the tripling as well, except for what would the 2 be? It would be a 3. Okay, now, can somebody answer B for us?
Yeah. I'll have the answer in 69 days.
Okay, so I heard ln4 over 0.02, or what? Yeah, aren't we just doubling again? Well, if it takes that much time to double, it doesn't matter whether we start with 500 and double to 1,000, or 1,000 and double to 2,000, or let's say there were 15,000 rabbits. How many days would it take to get to 30,000? 34.6 days. Okay? So that's the power of exponential growth. It depends on how much is present. Okay? Doubling is doubling. Okay? Twice as big is twice as big, regardless of whether we're comparing 5 to 10 or 15,000 to 30,000. It's still going to be the same. Now, this technique here works, doesn't it? Doesn't this give you the 69 whatever?
Yeah.
Okay? So we end up with 69 point, is it 32? 3-1? Okay, 3-1 days. Okay, any questions there? Sure? Okay, so let's take a look at a decay problem now. This is something that a lot of you may have heard of before. Anybody heard of radiocarbon dating? Okay. Okay, can anybody explain to us how that works? McKay? McKay watches a lot of History Channel, by the way. Go ahead.
Basically, you take how much carbon, radioactive carbon, in something and then figure out how much of it has decayed back into a more stable form, and you can get a rough estimate of about how long ago that thing died.
Yep, so it's all based on the percentage of carbon that's left in whatever it is. Okay? All right. So in order to understand how they do radiocarbon dating, okay, and we're actually going to do compute some formulas here, we want to understand that if something is radioactive, it decays. It decays into some harmless substance. It doesn't just disappear. It turns into some other type of substance that's harmless. Okay? So we usually keep track of the decay rate in terms of half-life. So we can turn it into a number that makes sense to most people. So there are some things that have a half-life of literally minutes. They decay really quickly and they turn into something that's harmless. Okay? There are other things that take a very long time to decay. They have very long half-lives. Okay? So here's what a half-life is. A half-life is the period of time required for a substance to decay to half of its original amount. So, as an example, let's say that I have 80 pounds of radioactive substance and it has a half-life of 3 years. What that means is, if we let 3 years go by, how much of that will be left? 40 pounds. Okay? So it's going to be 40 pounds. Now, that doesn't mean there's only 40 pounds there. What it means is there's 40 pounds that's radioactive. Okay? If I were a nuclear physicist, I'd be able to tell you exactly what happens to it. Okay? What if I let 6 years go by? Okay, now this is where it gets a little bit, I mean, this doesn't quite make sense. You let 3 years go by and we went from 80 to 40. You would think that if you let another 3 years go by, another 40 pounds would be gone, and we're done. It's gone, right? But it decays according to how much is present, just like the rabbits and the bacteria grow according to how much is present. Okay? So after 6 years, there's only 20 pounds. Okay, now listen carefully to what I'm saying. I'm going to let another 3 years go by. I'm going to let another half-life go by. How much do I have now? I have 10. I'm going to let another half-life go by, another three years. 5 pounds, another half-life, 2.5 pounds, and so forth. So at this rate,
Does it ever get to 0?
does it ever get to 0? Mathematically, using a mathematical model, it does not get to 0. It would be to the tiniest that you'd start dividing atoms and all that sort of stuff. Effectively, does it get to 0? The answer to that is yes, it does. Okay? Does that make sense? Okay, so that's how half-life works. And before I flip the page over, I want you to keep this in mind. How did we figure out the time it took to double? We had an ln of 2 divided by k. No. Okay? So think about that. If we know how to find out how something doubles, either the time or we can find the growth constant to figure out when it doubles, we should be able to do the same thing to figure out when it gets cut in half. So look at number 5. We've got iodine 131. It's a slightly radioactive substance. What did they do for us? They gave us the equation. Notice that what they've given us here, the negative 0.087, that is not the growth constant, it's the decay constant. Okay? And they've just reminded us, A naught is the initial amount and T is in days. So what it says is, what is the half-life? What is the half-life? In other words, nope, that's the decay constant. What this is saying is, how long does it take it before half of it is gone? So if I started out with A naught, how would I know when I got to half? 1/2 of A naught. So I'm going to do this. 1/2 A naught, e to the negative 0.087 times t. Now, take a good look at this. And again, we've talked about this today. I told you about this yesterday. Look at how we solve this. This is the way exponentials work. They're all based on how much is present at any given time. If I start solving that, Clayton, what do I do to solve that? Divide by A naught. So if I divide both sides by A naught, look what I get. I get 1/2 equals e to the negative 0.087 times t. Now, isn't it a half? Is it a surprise it's a half? When the other ones, when we were doubling or tripling or quadrupling, we had an ln2, an ln3, or an ln4 or something like that. So we're going to take the ln of 1/2 equals negative 0.087 times t. And how do I know what t is? We're just going to divide. ln 1/2 divided by negative 0.087. So what is the half-life? 7.967, and this is in days. So it takes, this is a pretty quick decay rate. It takes about 8 days for a half-life, for half of it to decay away. Now, everybody watch. Look at this. See the ln 1/2 divided by, what part of the formula was this? The decay constant. Look at this. ln2 divided by the growth constant. See how that works? That'll tell you the time every time, regardless of whether we're finding doubling time or whatever. Okay? We just need to know what we're putting in here. Is it ln2 for doubling? Is it ln 1/2 for halving or half-life? And so forth. Any questions? How long does it take 100 grams of iodine 131 to decay to 20 grams? Okay, let's stop and think about this, and let's take a guess before we actually figure it out. What if I let 8 days go by? What does that 100 pounds turn into? Or grams? 50 grams. What if I let another 8 days go by? That'd be 25. I want it to get down to 20. So I let about 16 days go by and I'm down to 25, so it's going to be a little bit more than 16. Everybody buy that? Now again, I've got some rounding in here, but let's look at how to solve this. So I want that 100 grams to turn into 20 grams. E to the negative 0.087 t. Same process over and over and over again, right? So I'm going to divide by 100. Notice what I've got here. What's 20 divided by 100? 1/5. ln 1/5 would equal negative 0.087 times t. So t is the ln of 1/5 over negative 0.087. You could probably recall on your calculator this one right here and just change the 1/2 to a 1/5. Type that in. Here's the exact answer. We're as close as we can get for this particular problem with what we've been given. What is it when you type in ln 1/5 divided by negative 0.087? 18.499 days. Is that in the ballpark of what we said it should be?
Yeah.
It is. Any questions? Sure? Okay. Now we're going to deal with, they actually do this, and these are legitimate numbers. McKay said you can find approximately. We know the exact half-life of carbon-14. Carbon-14 is in every living substance. You have carbon-14 in you right now. These desks, the tops, they're made of wood. They have carbon-14 in them. Okay? So what they do is, let's say some archaeologists are out, they're digging through some, they're excavating some remains and stuff like that. Maybe they find bone. Maybe they're digging up a campfire and they find some wood. Okay? Wood, okay, given a species or whatever, they know how much carbon-14 it has in it, like what percentage it should be of carbon-14. Bones, they know what percentage those should be of carbon-14. So what they do is they measure how much carbon-14 is left, and then they figure out, well, there's a lot less than there should be. Let's figure out what it is given the half-life, okay? So it says carbon-14 is a radioactive substance that decays according to that exponential decay formula that we've been talking about, if the half-life is 5,600 years. That's a long time. That's why they like using carbon-14. You can find something that's really, really old, and it will still have some of the carbon-14 in it, okay? So find K, then write a formula for the decay of carbon-14 if 100 grams are present initially. So let's see. They told us the half-life. They told us the time. We need to figure out what's K, what's the decay rate. So let's say I started off with 100 grams. If I let 5,600 years go by, how much would there be? If I let a half-life go by and it started out with 100, how much would there be left? There'd be 50. Now watch, this is going to happen the same way. Divide by 100. This is going to be 1/2. This is going to be E. I'm going to write 5,600 K. Notice the difference here. We're solving for K. We're not solving for time. But when I take the ln, I've got the ln of 1/2. This is 5,600 K. So that means K is equal to the ln of 1/2 divided by 5,600. And if you grab your calculator, we are going to use a decimal for this one. Positive or negative? It is going to be negative, and it's going to be, and let's do 124. Is that okay? Is that rounded correctly? 4 zeros and a 124?
Yes.
3 zeros? 4, okay.
Wait, what? Hang on, it's a 4.
Are you going to make me type this in the calculator?
No.
It's a 4?
Yes, it's a 4.
If you round correctly to 6 decimal places, there's our K. Now, if we know what K is, we can come back here and we can say, all right, you're telling me there's 100 grams present initially. So we found this bone, and it should have had 100 grams in it initially. E to the negative 0.00124, 24 times T. So I found, here's our formula. Here's our constant that we used to make the formula. And then it says, if an animal bone is found to only have 20% of the carbon-14 that it's supposed to. So, this bone was supposed to have 100 grams. How much does it have? 20% of that. So it's only going to have 20. So 20 equals 100, e to the negative 0.00124 times t. Okay, notice how this works. Could we have skipped ahead? Watch, please. Could we have skipped ahead and said, you know what? That's 0.2. This is e to the negative 0.00124 times t. Could we have skipped right there? Yeah, because they said 20% was left. If we set 20% equal to that exponential, it's a little bit easier. But again, this is a good thing to go through. Good process to kind of solidify in your mind. So this is going to be the ln of 0.2, negative 0.00124t. So that means t is equal to the ln of 0.2 divided by negative 0.00124. And so we end up with, this is, for this particular one, about what we can get for exact answers. And what have we got for an approximation there? 12,979. All right, I'm going to go this. Okay? All right. Any questions? Okay, stop and think about that again in terms of the previous problem. We wanted to know when it got down to 20 grams. It took a little more than 2 half-lives. If it takes 5,600 years for 1 half-life, that would be 50 grams. It would decay down to 50 grams. Another half-life would decay down to 25 grams. And we want it to get down to 20 grams, 20% of what it was originally. So we'd expect it to be a little bit more than 2 half-lives, and there it is, 13,000 years-ish. Questions? Okay. Let's look at a couple of interesting problems then.
Would you get burned? No, not at all.
What are you reading?
It's a story problem.
Oh.
How many bakers do we have here? Has everybody baked a cake before? Cookies, stuff like that? Okay. So, most of the time you bake things at about 350. So if you put a cake in the oven, bake it at 350 for the 45 or 50 minutes or whatever it happens to be. Take it out, put it on top of the stove, and then take your hand and put it right on the cake. Not the pan, but the cake. Will it burn you?
No.
It would take a while to burn you. Now, if you touch the pan, will it burn you?
Yeah.
Okay. And that all has to do with thermal mass and all that sort of stuff. Is it hot? It's pretty hot. Now, what if you let it sit there for 5 minutes or so and then come back and touch it? The pan's still going to be pretty hot. What about the cake? It's going to be better, okay? Now, guys usually don't know the answer to this. How long do you have to wait before you can frost the cake?
Oh, it depends. Do you want to put it in the fridge to speed up the process?
Okay, we're going to go with room temperature, okay? You have to wait until it's completely cool, because even the outside will cool pretty darn quickly, okay? So the temperature will, it actually isn't at 350, it's probably at 200 something, okay? But it's going to go from this really high temperature that's pretty darn hot, it's going to drop down pretty rapidly. But to get to room temperature, it takes a long time. Okay, you can come back an hour or two later and you can feel the cake. It's not going to burn you, it's not going to feel hot, but you can still feel the warmth inside. And what happens if you put frosting on a slightly warm cake? It melts, okay? So you have to wait a long time. If you want to put it in the fridge or the freezer, that can speed up that process. By the way, if you're decorating a wedding cake or something like that, you know how they get the frosting not to tear off the top layer of the cake? they freeze them. So they decorate them when they're frozen. Okay, makes it a lot easier to work with. Okay, so that's something called the fact that it changes very rapidly and then kind of levels out toward room temperature. What does this look like? Exponential decay. Okay, so this is called Newton's law of cooling. All right, so we're going to run through and we're going to talk about what each one of these things is. Now, think about this in terms of a cake. We're going to take it out. It's going to be pretty darn hot. It's going to have its own temperature. We're going to set it on top of the stove or on a cooling rack or something like that. Once it comes out here and levels off, what's it going to level off to? What temperature? Room temperature. Guess what the R stands for? Okay, so this is room temp. Guess what T naught? Now this is a capital T. Initial temperature. Okay? So R is room temperature here, and this is the initial temperature of the cake. Guess what this little T is? Time, just like always. And guess what the K is? We'll call it the cooling constant. Okay? So all you need is room temperature, the initial temperature, and the cooling constant, and you've got your formula. So let's take the information here, and let's see if we can figure this out. A cake is removed from the oven and placed on a cooling rack in a 70-degree kitchen. That tells us something. The cake's initial temperature is 250 degrees. That also tells us something. After 10 minutes, so they're giving us a time, the cake has cooled to 210 degrees. So it's cooled off a little bit. Okay. I made these numbers up, by the way. Okay. The cake can be frosted when it reaches 75 degrees. So the first question is, what is the formula for the temperature at any time? So let's find this formula here. And the second question is, how long will it be before we can frost the cake? When's it going to reach 75 degrees? So here's what we do. Okay, what is R? Room temperature, 70 degrees. Okay, plus, what is T naught? What is the initial temperature of the cake? 250. Minus, what's room temperature again? 70. And then it's going to be e to the KT. So here's what we've got. T equals 70. Now stop and think about this for just a minute. This looks like an absolutely nasty formula. Okay? Does it make sense that the number in front of this decay factor, this exponential decay, has something to do with the difference between the two temperatures? Okay? Kind of like a vertical stretch or shrink. So this is going to be plus 180 e to the k times t. Now, what's the problem with this? Yeah, or at least way too many variables, right? So let's take a look at this other part of the problem. After 10 minutes, the cake is 210 degrees. So if you put 10 minutes right here, what can you put over here for the temperature? So we're going to do 210, 70, plus 180, e to the k times 10. With me there? First step, move the 70. So this is 140 equals 180 e to the 10k, I'll write it. Next step, divide by 180. Okay, now I'm going to do this. Everybody watch, please. I'm going to cancel the zeros, and I'm going to reduce that by a factor of 2. This is going to be 7/9 e to the 10k. ln 7/9 equals 10k. So that means k equals the ln of 7/9, all that divided by 10. And we throw that in the calculator and we get a decimal for that. Okay, before you hit enter, is the answer going to be positive or negative? Negative, because it's decaying. The temperature is going down, right? So we get negative 0.02513. 131. Okay, there it is. Now, I'm going to come over here, so I'm going to make this smaller again. Here's the answer to part A. The temperature is 70 plus 180 e to the negative 0.025131 times t. There's the answer to part A. There's the formula that will tell you the temperature at any time. What temperature do we want it to be?
75.
So we'd say 75 equals 70 plus 180 e to the negative 0.025131 times t. Move the 70 over, divide by 180, take the ln, divide by negative 0.021, well, that sort of stuff, and that'll spit out the answer. Okay, are there any questions? Okay. I'm going to let you finish that. I'll write the answer in just a second. And then we're going to just look at this last little part. And I'm going to have you read a couple pages in the book. Okay. Anybody got that?
It's 142, 559 minutes.
Which sounds pretty reasonable to me. It does take several hours for stuff to cool off. Cookies cool off really, really quickly. Cakes, not so much. Anybody tell us why? Mass, it's the pan, it's the inside of them, all that sort of stuff. If you throw a cookie on a cookie rack, it's pretty thin. There's not a lot of thermal mass. It's got a lot of air moving around it and stuff like that. It's going to cool off a lot quicker than a cake is, which means if we were to come up with Newton's law of cooling for a cookie versus a cake, what's going to be different? Time is, but the big part? Even if it came out at 250 to begin with, it's going to cool faster, so it's going to have a different cooling constant. Okay? All right. Last thing I want to look at, and I just want to talk about this idea. It's pretty unreal. So I need everybody's attention for just a second. It's pretty unrealistic to think that everything can obey the law of uninhibited growth. So if we're talking about those rabbits again, okay, even if you go down to Delta, okay, there are tons of jackrabbits down at Delta, but they can't continue to grow because they run out of food, they run out of water, they run out of space. Even in a bacteria culture, if you put that stuff in that gel, what's that called, agar? Okay, when you put that in there, you could have tons of bacteria in there, but sooner or later they're going to die because they're going to run out of food, water, and space. Okay, so things normally don't grow that way. Normally there's some cap to how much they can grow. So a more realistic growth model is something called logistic growth. And I'd like you to read a couple of pages. It's 481 to 484. Sorry, 481 to 483. And you're going to look at problems that look something like this. Okay? This would be a more realistic growth model. Okay? It looks uglier. It's a little bit more difficult to work with, but here's how it works. If I said, this is about rabbits, right? How many rabbits are there to begin with? How could you find that out? Plug in. What does T stand for? Time. Plug in 0 for the stopwatch. So if I plug in a 0, this is going to be e to the 0, which is 1. This is going to be 49. 49 plus 1, 50. 250 divided by 50. 5. 5 rabbits to begin with. Okay? Now, it says we've got 5 to begin with. And then what's going to happen is it's going to reach something called its carrying capacity. Now, if you had to guess, looking at these numbers, this is a farm. It's only capable of supporting so many rabbits. What would you guess is the carrying capacity of this farm, or the maximum number of rabbits? It's going to be this number right here. It's going to be the 250. Okay? And what's going to happen is if we were to graph this, We're going to start out at 5. It's going to look like exponential growth, and then all of a sudden it's going to start to slow down, and it's going to level off and have a horizontal asymptote. Where would this asymptote be? At 250. Okay? All I want you to do is just read those. The formulas are not that bad to work with. That's it for today. Quiz tomorrow. Quiz tomorrow. So make sure you come with questions that we can get out of the way before we take that quiz. I will have the review online, and I'll have a copy of it for you tomorrow. Review Thursday, test Friday, off for spring break. Okay?